A rational function is defined as the ratio of two polynomials. So here we have an example of one f of x, where there's a polynomial in the numerator and the denominator, and ratio just means we're dividing those two things. Let's try to figure out what the graphs of these equations look like. So this probably is too difficult to start with, so let's focus on just y equals 1 over x. One feature that these graphs will have are things called asymptotes that I'll try to describe in this simpler equation. So to start with, you can just go to your graphing calculator and in place of y1 enter 1 divided by x. I'll do that too. And it's not a very clear picture, but I see something happening over here, kind of like disappears. And then there's something on this side as well where I have some negative y values. You could go to your table and follow along, but I want to describe why the graph looks the way it does by choosing some values for x and figuring out their corresponding y values. I'll start simple by looking at x equals 1, 2, and 3. If you put 1, 2, and 3 into the function 1 over x, starting with 1, you get 1 divided by 1, which is 1. For 2, you get 1 divided by 2, or it'll give you a decimal of 0.5. And if you type in 3, you get 1 divided by 3, which is equal to 0.3 repeating, which is a third, obviously. So on your graph, at x equals 1, you get 1. At x equals 2, you get a half. At x equals 3, you get a third. And I see what's happening. As we're moving this way, the graph gets closer and closer to the x-axis, which is y is equal to 0. Now, if we go in this direction, you're going to enter numbers like a half, a third, and a fourth. And what we'll see is the graph is going to get bigger and bigger and bigger. So by that I mean, at 1/2, 1 divided by a half is 2. At a third, 1 divided by a third is 3, and so on. So at a half we got 2. At a third we get 3. At a quarter we get 4. Okay, I see. The graph gets larger and larger and larger, and that never ends. So what's happening over here is the graph goes up to positive infinity and it keeps getting closer and closer to the y-axis. And this way, the graph gets closer and closer to 0 and it approaches the x-axis. So if I were to now sketch in my graph, like it's not going to be a perfect picture, but I'll just put this arrow to say the trend continues. And I'll do the same thing in this direction as well. Now, for negative x values, if I just put negatives in front of all of those, I get negative numbers over here. So that's why you see the graph is now below the x-axis instead of above it. But the same principles hold where, okay, it's going to go towards minus infinity, and it's going to go towards 0 on this side, going through those points. And there is my graph. You get a better graph if you zoomed in on certain portions of it, but I think this is good enough to illustrate what it's doing. Okay, now talking about this idea of an asymptote. Like I said, the graph is approaching the x-axis. So I'm going to say that y equals 0, which is the x-axis, is an asymptote. And more specifically, it's a horizontal asymptote. It's a very fancy way to say that the graph gets closer and closer and closer to y is equal to 0. Likewise, the y-axis, or x is equal to 0, is what we're going to call a vertical asymptote. Clearly, the graph keeps getting closer and closer to this thing. So ahead of time, if you know the location of these types of asymptotes, it's really easy to get an idea or a sketch of the graph. You can plot the asymptotes and then say, well, okay, my graph has to approach these places. So we'll use this idea when sketching more complicated rational functions. So speaking of which, let's look at this one. F of x is equal to 2x plus 4 divided by x minus 2. So I'm going to my calculator and I'm actually going to graph this thing in place of y1. And I'm going to be careful here. You have to use parentheses around the numerator and denominator to tell the calculator that, okay, we're dividing x minus 2 into, all of that into the entire numerator. If you leave off the parentheses, it'll not give you this graph. Anyway, what I'd like to do is determine where are the asymptotes on this equation ahead of time. If you know that, you could plot the asymptotes wherever they are, and the graph has to approach those places. I'm going to throw in one extra idea too. not only asymptotes, but can we also figure out where the graph is crossing over the x-axis and the y-axis, just for a little bit more guidance, a more accurate picture. I'm going to try to do all of this by just using numbers that appear within the equation and my graph to justify it. So I just put this thing in place of y1, and I'm looking at my screen on my calculator, and I can see there's this vertical line on the graph that appears, it looks like it's really close to x is equal to 2. So it looks like there's a vertical asymptote here. The graph also appears to, level off a little bit, so there's definitely some type of horizontal asymptote over here. The graph is also crossing over the x and then the y-axis, and it looks like that's happening around maybe -2. I'd like to somehow see how the numbers up here determine this on the graph. I'm going to start with the vertical asymptote, which I'll just abbreviate VA. All right, so the vertical asymptote is actually not part of the graph, and that's going to be wherever the denominator is equal to 0. If you put 2 in place of x, you get 2 minus 2, 0 in the denominator, and division by 0 is undefined. That's why you get this weird thing happening on the graph at x is equal to 2. Division by 0 will result in a vertical asymptote in this graph. So I'm just going to go ahead and put that on here. And I'm going to use this as a fact from now on. This is where the denominator is equal to 0. And we can use this on more complicated rational functions too. If we know the denominator is 0, that's going to result in a vertical asymptote. All right, what else do I see? That's where the denominator is 0, but what about where the numerator is 0? What would that tell us? I can see that if I put -2 in place of this x, it's going to make the numerator equal 0. And at x equals -2, I actually see that there is an x-intercept. The graph is crossing over the x-axis. So I'm going to label that as well. So if you want to find an x-intercept, this one is at -2 for x because it gives you 0 back for y. And this is where the numerator is 0. So again, that's a useful fact. You can just look at this equation and say, oh, 2 in the denominator gives me a vertical asymptote. -2 in the numerator makes it 0, giving me this x-intercept. So 2 more things. Is there a y-intercept? I think that one will be pretty easy to find. If you want to find the y-intercept, you can go to your equation and put 0 into all the x's. That'll tell you the y value of x is equal to 0. If you put 0 in place of every x, that's f of 0, it's going to cancel this 2x and this x, leaving you with 4 over -2, which simplifies to simply -2. That's 0 for x and -2 for y, which is right here. All right, so what's really happening is the ratio of the last 2 numbers will always determine your y-intercept. So I'll just put that as a fact as well. This is the ratio of the constants, the numbers at the end. So ahead of time, if you knew that, you could have said, oh, 4 over -2, that's -2, that's the spot here. So this leaves us with one last thing. What is the horizontal asymptote, and how can I figure that out? Just by looking at the graph. And I state it as a fact up here. The horizontal asymptote is going to be equal to the ratio of the numbers in front of the highest powered x terms. It's quite wordy, but to see that in this graph, here are the highest powered x terms. In the top we have a 2x. It's not written, but in the denominator there's a 1x. If I take the ratio of those 2 numbers, that is y is equal to 2 over 1, or simply just, y is equal to 2, same thing. This will be the horizontal asymptote. And once you know these things, getting an accurate picture of the graph is very easy. I'll sketch that on here now. The graph has to approach the asymptotes, and it also has to go through these intercepts. And likewise, I see the graph exists up here as well. I'm just trying to get a decent sketch of this equation, and this is what I have. Okay, so to recap, If I look at this equation, where the denominator is 0 tells me the vertical asymptote. Where the numerator is 0 told me the x-intercept. The ratio of the last two numbers told me the y-intercept, and the ratio of the first two numbers told me the horizontal asymptote. It's pretty easy to justify most of these. This last one's a little confusing, but we can definitely talk about that in class. And that is it for this example.